All right. Okay, so we are going to restart the tutorial. So I just for the benefit of those who just join in over the live stream, I'm going to do another reintroduction. So I'm Hady. I'm from Singapore Management University, and with me today are the other two speakers. Tuan is also online. He's also from the same university as I am. And those of you who are lucky to be in Amsterdam, you will be with Aghiles. He's in front of the stage there. And so in the course of this tutorial, you're going to be hearing from the three of us. Now, we will firstly tell you a couple of reasons why this tutorial is interesting, and I'll tell you three reasons. One is that because it's going to be on multimodality, and what it means is that is multiple modality. So we're going to talk about text data, we're going to talk about images, we're going to talk about graph. So that introduces some degree of variety to the kind of models that we're going to be looking at today. So it's not just preferences and interactions alone, but also there will be some content information along with it. Now, the second reason why it will be interesting because it's going to be a hands-on tutorial. So hopefully you have your laptop with you. If you do, then you're going to be able to follow along in some of our hands-on sessions where we will provide you with a Jupyter notebook. And this notebook is going to give you like a step-by-step instruction as well as some codes that you can use to essentially get a sense of what this tutorial is about. So in a way, it is quite practical because after this tutorial, there are going to be some take-home codes that you can use to build your own multimodal recommender systems. And a lot of the algorithms that we're going to talk about today would have been implemented inside Cornec, which is a Python-based library on multimodal recommendations. Now, in case you're wondering where the materials would be, so if you go to the very top of a slide, right? Every slide is going to have this link. That's going to point you to our page where we give the information about the tutorial itself. And then there's going to be a link to a GitHub page. And the GitHub page is going to have the slides. The slides essentially what you're looking at now, as well as the codes, right? The links to the notebooks that we're going to use as part of the hands-on. All right. So far we talked about two interesting things, right? Multimodality and hands-on exploration. And the third thing is that as we go through this, it's also kind of like a survey into some of the recent models on multimodal recommendations. So we're going to give you pointers and references in terms of these papers. And therefore, you're going to have some take-home reading as well that you could use to build up your familiarity with this area, which is a fast-growing area. And we hope that in the future, as we discuss more and more of multimodal recommender systems, we will begin to see some of your work as well within this survey. Okay, so to get started, we're going to let's take a look at the kind of outline that we expect to go through today. Now, in this case, the first part is going to be an introduction to recommender systems and multimodality. So essentially, you might already be familiar with recommendations. We're going to tell you what we mean by multimodality. And in this case, one of those modalities is going to be preference data. And the other modalities might be some other content that come along with either the user or the item. Now, beyond the introduction, which is kind of like a gentle introduction to set up the framework as well as to set up the scope of what we're going to be talking about today, then we're going to take you to Cornec. And this is going to be a hands-on exercise where we will show you a notebook that you can run, and we're going to discuss the notebook along with you. But the idea here is that Cornec is going to be a recommendation library that makes it very easy for you, first of all, to deploy, implement, or to essentially build a model, a multimodal recommendation model. And it also makes it easy for you to compare, because we built in this feature to easily run multiple models and then compare them along the lines of, within against the same data set, against multiple metrics. So in a way that, those of you who are working on recommendations, you realize that a lot of it, to some extent, depends on the data, and you might want to look at different models and compare their effectiveness. And Cornec is pretty good at that. So you're going to take a look at what it is able to do. Now, and then we're going to go into the meat of the tutorial itself, which is going to be a discussion on three respective modalities. Now, before the break, we probably only have time to go through the text and images. These are going to be two modalities. They can enrich recommendations. And then after the coffee break, we're going to go through the third modality, which is also a very important modality. I think graph information, graph data is now one of those, the most active research areas as well. I think just a couple of days ago, we heard the keynote on graph neural networks as well. So I think you will probably appreciate the usefulness of graph. So do come back for the graph modality discussions as well. And then we're going to have two hands-on parts that talk about two different aspects. Now, multimodality is the idea that let's take a look at specific examples. We talk about text, images, and graph, and we're going to give you specific examples of what does it mean to work with text, what does it mean to work with image, what does it mean to work with graph. Okay, so that's what we mean by multimodal. Now, interestingly, we would then go on to the third hands-on, which is going to take us to a novel direction in the following sense. I think if you think about a lot of the models that people are discussing today, I mean, when they talk about text, they only talk about text. When they talk about images, they only talk about images. But what we find within our own exploration and observation is that a lot of the models that people design for text could also be used even when you're dealing with image data, for example. And image models could be used for graph data, and graph models can be used for text data. So in a way, these different modalities, they are not that different. I mean, of course, they are distinct modalities, but there are some level of commonality between them that allows some of these models that is developed for one particular modality to be cross-utilized with other modalities. So that I think is going to open up our horizon in terms of when we think about what models to use. We're no longer going to be constrained just by thinking, hey, I have text data, and therefore I have to go to only this model because this is a text model. But it turns out that when we look at other modalities like images and graph, then they will also have models that are applicable to the task at hand. So in a way, I think what you're going to see in this tutorial is going to be an overview of the different things you can do with the respective modality. And particularly, I think we would like to also take you to this journey of being more open-minded in terms of what we consider to be modality and which models we should be considering when we want to work with certain type of recommendation problems. All right, okay. So, okay, then I'm going to just first of all give a quick run through of why we are interested in multimodality. And this necessitates also a discussion of some basic models that probably are very familiar to many of you, because we're going to talk about some of the basic recommendation models, but they become a building block. So when we are going to talk about adding text, we're going to talk about adding text to some underlying fundamental model, which could be like matrix factorization or Bayesian personalized ranking and this sort of models. All right. Okay, so the idea of recommendation is not foreign to us. And we understand that the primary reason why we need recommendations is the number of possible options that we would have to deal with whenever we go online. And I'm not just talking about e-commerce, I'm talking about anything that we do online, finding news articles to read, buying a product online, looking at different images that you want to use for your website, and things like that, right? There are just so many options, and we can't possibly consider every one of them. Then, of course, if you know what you're looking for, then maybe you can put in some keywords, right? And that is essentially a problem of retrieval. But even so, even when you know the kind of keywords that you want, and you post those keywords, chances are you will still get too many options. So for example, if I'm looking for men's shoes, I might know, I mean, to the level of vocabulary that I have, I may be able to describe the kind of shoes that I want, but chances are there are still too many possible varieties. This is just the query results for men's shoes on Amazon. There's like 100 over 1,000. And if we even look at some of the bigger e-commerce markets, like Taobao in China, it can easily throw out 4 million results, for example. And that's kind of is an issue if there had not been recommender systems. But the reality is that recommender systems have been in place for a long time now. and they are deployed in multiple different variety of applications, right? And different domains. I mean, e-commerce is just one of them. If you watch things on YouTube, if you are trying to book hotels, if you're trying to find restaurants, even if you're trying to find a friend and things like that, and you're going to get a lot of these recommendations, right? Now, the key problem that recommender systems usually have is the shortage of data. I think we usually call it the cold start problem. And the cold start problem begins with the idea that a lot of the users are probably new to the system, or a lot of the items are new to the system. Because, for example, I don't know, every day there are so many new videos on YouTube, new users to LinkedIn. I mean, a lot of these online users, online systems are still growing. So they're gaining users. So which means that at any point of time, many of the users and many of the items are new to the system, which means that we don't actually have a lot of information based on their interaction data alone to provide these recommendations. And therefore, this is where we see the role of multimodality to come in, because then we have to consider other sources of information that can supplement this. Now, if we are going to look at this problem, because we're going to introduce some of these models later on, right? I just want to motivate, like there are several different ways of thinking about recommendation problems, and we're going to touch on them over time, right? Of course, from the angle of multimodality. Now, sometimes we are dealing with a rating prediction problem. In this case, you are interested in predicting the rating between a user U to an item I. So in this case, we are going to develop essentially a function that is going to predict a continuous value. And the continuous value is going to be a measure in terms of how much a user likes an item. Now, in some other cases, we might be interested in a ranking. So ranking would mean that we are not so much interested in exact scores. We just want to know in relative terms, if you give me two items, which one I would prefer to the other one. And this is the backbone of some of the recommendation models. And the way that the models are going to be developed are going to be a little bit different between the two. Because in one cases, we might be optimizing for the accuracy in predicting rating. In the other case, we might be interested in optimizing for the correctness of the predicted rankings. Now, the other thing that people keep talking about is the idea of collaborative filtering versus content-based filtering. And the basic difference here is that collaborative filtering is based on preference data. So if we consider two users to be similar, if they have been interacting with the same items, like movies or product and so on. In the content-based filtering, we are going to make use of similarity in content. So for example, a user may watch a movie, and then we're going to recommend other movies that are similar to them. Now, at this point of time, I would like to pinpoint the idea of multimodality. I think it's kind of like preceding what we're going to discuss shortly. But the basic idea of multimodality is multiple modality. And here, we would put forward that the modalities that we are most concerned with is going to be the modality of preference and interaction data, which is given by the collaborative filtering, and the modality of the content, which is the content of either the user or the item, that allows us to also draw similarities across items. So when we talk about multimodality, in a big way, what we're really talking about is going to be the interplay between both paradigms. So in a way, one perspective of multimodal recommendation essentially is a unified view of collaborative filtering and content-based filtering. They can integrate both points of view within a single model. And that's what makes it interesting, because then it means that we have multiple sources of information to essentially solve the problem. All right, so everybody knows Netflix price. I'm not going to belabor what Netflix price is all about, but it's just to pinpoint the winners on Netflix price. They kind of say that the most important models, at least what happened then, were the factorization models. So we just want to put all of us on the same page that matrix factorization is going to be one of the fundamental building blocks. In the case of matrix factorization, we have users on one side, items on the other side, and we have a matrix of their interaction, like ones or zeros or minus one, or essentially any value. They indicate a measure of liking or a likelihood of adoption. And this matrix is going to be very sparse. And therefore, in order to fill in the missing values, one approach is to do a factorization. So factorization means that from the matrix R, we're going to decompose it into two sub-matrices, much smaller matrices, U and V. U for the users, V for the items, such that when we multiply the latent vectors together, they're going to give us a more complete matrix, including filling in the values that didn't used to exist in the original matrix. And those new values are going to be the predicted ratings. Okay. And the way that is done essentially is the latent factors. Now, if you find all this familiar, I'm sorry for belaboring this, but actually I just want to put us all on the same page because we're going to make use some of these models as the building block for the multimodality. Okay, so you just just give it a sense that you're looking at standardization of the notations that we're going to be using so that we are all on the same language when we are talking about multimodal recommendations. All right, so we are going to try to estimate the latent factors, which are the U's and the V's. And these are going to be done by minimizing some loss function. And in the case of the rating prediction problems, the loss function that we minimize essentially is the squared loss. So which means that we are looking at the predicted values and we see what is going to be the difference to the original rating. And the thinking is that if they are very close to the original rating, then chances are the new predictions that we have would also be a good prediction for the unobserved values. Now, the issue with fitting in these values directly or in an isolated fashion is that the original matrix was sparse to begin with. So which means that we might end up with a lot of overfitting issues. And therefore, what is a common trick to do is that of regularization. So regularization simply means that we are going to take those latent factors that we want to estimate and we regularize them and we make sure that their values are not going to run away. In fact, in a way, it's like giving them a prior. So that we try to constrain them using the regularization terms such that we get a simple model that can still have a good prediction power. Okay, sometimes we have factors that are specific to the user, specific to the items. We're going to call them user and item biases. And these are usually used to model the idea of item with a high bias are usually popular items that everybody likes. So that by default, you give it a high rating because everybody likes them. Item with low bias, then it could be items that are less popular or that everybody hates. And therefore, by default, you give them a low rating. So in a way, user on the other side have a similar type of behavior. Some users tend to give always high ratings. Some of the users will tend to give very low ratings frequently. Okay, so now what we talk about essentially is what we call explicit feedback because we kind of explicitly say what the rating is going to be, and then that becomes the basis for predicting future ratings. In some cases, we might be a lot less confident about the kind of data that we're dealing with. So the preferences might be unclear or that it's going to be noisy. So we get some signal, they give us some relative signal of something is preferred to another one, but it's not a definitive or a very clear signal. And I'm going to just talk about two models because these are going to be two models where we are going to expand later on with the additional modalities. One model is called weighted matrix factorization. Essentially is still matrix factorization, the way that we think about this earlier. But the interesting thing about this is the factor of confidence. Here there is a parameter called confidence. This is usually given. And the idea here is that what we are observing essentially is a confidence value, not an actual liking value. So meaning that, for example, if I'm going to try to predict whether you like a movie, I might see the number of times you watch the movie as a degree of confidence. Because, it doesn't mean that if I'm going to predict, I don't want to be predicting how many times you watch a movie. I probably just want to predict whether you're going to like a movie, even if you watch it only once, right? So in that case, maybe the times in the past that you have watched the movie a lot, it just gives me lots of confidence that you might like the movie. So this changes the way that we're going to optimize the model a little bit, because now it's not so much the accuracy alone that matters, but essentially all observations, which here by P we mean the adoption, is going to be weighted by a degree of confidence. For some items, you're going to be a lot more confident, and therefore we're going to place a lot of emphasis on getting it right. For some other items, maybe we're not so confident, and therefore we're going to put less emphasis on getting it right. Now, the other type of implicit feedback, I think this is also a very popular model that a lot of people in RecSys probably know. It's called Bayesian personalized ranking. And the key idea is just that okay, you observe all these ratings or the number of times someone watches a movie or listens to music and so on. These are not exact values that we are trying to predict, but it gives us a sense of ordering. So if I watch a movie 20 times, let's say, not that I do that, but okay. But let's say if I watch a movie multiple times, I probably like it more than a movie that I watch once. Now, the figure 20 is not as important as the fact that it is more than one, for example, right? I mean, we are interested in the relative sense of how things are ranked. In that case, we are concerned with what we consider to be triples. So triples, for example, are things like this. Like we say, given a user I, we are looking at two different items, J and L. And then we want to maximize the probability that the user is going to assign a higher rating to J than he is going to assign to the rating of L. Now, but we don't care the exact value of those ratings. We just care that J is greater than L, right? So that is another different way of looking at implicit feedback. Now, those were the matrix factorization, and a big part of what we're going to talk about are still on matrix factorization because they are still pretty competitive. Even with the emergence of a lot of deep learning models. But it's not to say that we're going to overlook the deep learning models completely. And if we just were to mention two of them, I think one is the neural collaborative filtering. Here, the idea is to use neural network to essentially be a generalization of the regular matrix factorization, where matrix factorization is a completely linear model. In the case of neural collaborative filtering, we can make use of nonlinearity, just like what a neural network could do, in order to hopefully fit the data better, right? So this is one such model. A different kind of model is essentially based on autoencoders. I think VAE or variational autoencoder has shown pretty good performance in recent papers in terms of recommendation problems. So you're probably familiar with what VAE is. So the idea is to encode the information, let's say in this case, the user information in terms of the different items that the user has adopted in the past. And we're going to encode it into a distribution. And from that distribution, we're going to sample it again. And when we decode it, we get a fuller expression of the user's preferences over the full range of items. And the AVA is robust enough to kind of look at the similarities across the users in such a way that it is actually showing pretty good performances. Now, the only thing about the original VAE is that it presents a one-directional view because it is looking at encoding users' information. But if we think about matrix factorization and the prior models in terms of recommendations, what we realize is that users and items are actually pretty symmetric in the way that we're modeling them. Because in a particular matrix, right, so one's going to be one axis, the other one's going to be the other axis. So it is much more natural to think of users and items as essentially having equal standing in the context of recommendations. And therefore, there is also another recent model, which coincidentally is authored by the three of us, which is called bilateral VAE. It appeared in Wisdom this year, that looks into this issue of bidirectionality of relationship in terms of users and item. And in this case, then we designed a VAE-based model that would respect the two-way nature of user-item interactions. And it turns out that the results are actually better than if you were just to look at this in a one-directional way, like the original VAE does. Okay, now all those things that we talked about earlier are just the base models for the preference data, the recommendations part of it. Now, what we're going to do is to go beyond that. So, I mean, those are the things that essentially the recommender systems community already are actively involved in. We want to base on those kind of models, but take them into the realm of multimodality. And the motivation to do that is the idea that for a lot of the data that we are dealing with today, we actually have a lot more information. So for example, if I'm looking just like like in this case, like a polo t-shirt, there's going to be additional information about the item, right? So for example, you might have some text that talks about the descriptions of the products. There is going to be an image And the image is, in this case, because it's a fashion item, it is a good representation of what kind of a product it is, right? And at the same time, there are also relationships among products. For example, if you go to Amazon, they will tell you, okay, if you're looking at this, maybe you're also interested in all these other things. So which means that these other polo shirts are in one way or another related to this. I mean, they're kind of similar products, substitute products, but in a way, they are also products that customers usually click together, right? So that gives us additional information in order to drive the recommendation forward. And this is what we kind of think of in terms of modalities. So one is text, the other one is image, and the other one is going to be graph in terms of the relationship. Now, it also applies to music, right? But we are not actually going to discuss music a lot in this tutorial. So I'm just going to skip this for now. But the other point that I want to make is that it's not just items, but we also talk about users. Users also have a lot of information. And the things that we talked about items earlier also apply to users. Users also have text information. Their images, what they look like, and they are connections, like they're friends, right? So in a way, both of these both sides, user items, they both have modalities that we can factor in. Okay, so now, without belaboring the techniques, right, for now, because I think we want to get into the models, the idea here is that we're going to work with 3 modalities. One of them is text. And in the simplest case, a lot of people think of text in terms of term vectors, like TF-IDF values. This could be one representation, but the idea here is that there's going to be some vector representation that you can use to represent text. So one case is TF-IDF, another case could be something that you get, let's say, from word vectors, word embeddings, and so on. Graph as well. I mean, we think of graph as a 2-dimensional information, like users on one side, users on the other side, or items on both sides, right? But in a way, if we look at the neighborhood information, then in this case, every item or every user might have a vector of connections. So in a way, we can think of them as also being represented by some vector for every user, every item. And images are the same, right? Either we work with raw data like pixels, or we work with some hand-identified features like SIFT features. These are essentially just feature vectors that eventually we're going to make use of in order to derive the modality. Now, but this is not just, these are some basic ideas of how to represent text, images, and graph. Chances are, in today's age, right? I mean, we are probably going to rely a lot on feature extractions that are driven by some of the deep learning models. For text, I think word vectors, recurrent neural network, nowadays transformers. Images, we might be dealing with different versions of convolutional neural networks. For graph, of course, there are also graph embeddings, graph neural networks, and graph convolutions, and so on. So all these things are essentially just a way to extract features from text, images, or graph. Now, the important thing essentially is the key thing of what we are going to delve into for the remainder of this tutorial, which is we are going to integrate this collaborative filtering, that is the idea of preferences, and then the content-based filtering, which is the idea of the content. And the content will be either text, images, or graph, okay? Yeah, so now it turns out that this is a good thing to do for 2 reasons. One is that it can be done relatively easily, I mean, with some engineering architecture changes, because matrix factorization and deep learning are both very modular and extensible. So then we can actually bring them together and create bigger and better models. And the second thing is that it's better because now we have a second source of information that helps us to improve the performance. And I think you will take a look at some of the hands-on tutorials. You will see that in each and every case, we generally get a boost in performance when we are dealing with an additional modality. Okay, so now without further ado, right? So we are going to go directly into the multi-modal recommendations. Of course, we are going to start with a hands-on tutorial, because we want to get you, quickly a sense, like some hands-on trial, so that you can experience some of these libraries, and you can see how easy it is to build a new recommendation model, even one that is going to be multimodal in nature. Okay. Now, at this point of time, I would actually pass it on to my co-speaker, Aghiles.
Yeah. Thanks, Hady. I think we need to switch into the slides in the room, so as I can take over. Yeah, great. Hello everyone, thanks for attending this tutorial, either virtually or physically. So for this first hands-on, the objective is to get started with Cornec. So if you have a laptop with you and you want to have a look at the notebook, at the link, please feel free to visit the link. But before, let me just give you an overview of what Cornec is and why we have developed this framework. So this is a Python-based recommendation framework, which is open sourced by Preferred.ai, which is a research group at the Singapore Management University led by Hady Lauw. And if you are interested in a less technical and a more intuitive introductions on the main objectives of this framework, you can have a look at the GMLR paper at this link that describes the purpose of this framework. Okay, so here is an overview of Cornec. So there are mainly 5 main modules. There is the data module that will help you to handle different types of data and modalities. You have the Cornec models, which actually offers a rich collection of recommendation models, both the one integrating additional data and the basic models, which are good baselines to assess if adding some new information brings some additional value. And then you have the evaluation method module that helps you prepare your data to run an experiment. You have the Cornec metrics, which actually comes with a number of commonly used metrics to assess the effectiveness of your recommender models. And finally, we have this experiment module that will actually bring together all the instantiation from the other models to run an experiment in a very convenient way. Okay, so one key feature of Cornec is multimodality support, both for reading, formatting, transforming, and representing different data types. So as you don't have to write the code to prepare your data every time, you have to deal with one of the 3 modalities that we are talking in this tutorial. It also offers a way to conveniently to develop new models in a convenient way, in the sense that it offers you the modality modules that helps you if, let's say, you want to develop a new model integrating image, then this will make it much more easier than if you have to build everything from scratch. And it also allows to broaden the use case of existing models. I think at some point Hady mentioned about this notion of cross-modality. Let's say you have a model that initially works with image data, but you don't have images available, you have graph data. It doesn't necessarily mean that you have to change your model. You can actually just adapt this model to work with the graph data better than ignoring it. So Cornec will actually make it very convenient to do this kind of operations. And then it also, there are also a number of things in Cornec that helps you build scalable recommender models. Those are iterators for easy stochastic optimization, either on the user side, item side, or the user item ratings. We also harness the Python ecosystem as much as we can using NumPy and SciPy, for example, for efficient matrix operations on sparse matrices and other related operations. And we also use for certain models a lot of Python, which helps to get comparable performance with C, C++ code. And finally, accessibility and reproducibility. Currently, there are over 40 models available in Cornec, and we welcome new contributions. We also try to make it easy to make use of benchmark datasets, and then also give a full control over the random number generators, so as you can make sure you can reproduce the results of your experiment exactly. Yeah. This is a very experiment-oriented library, which means like if you took a look at the notebook, then you realize that you have a data loading part followed by the evaluation method instantiation. Then you choose the models you are interested in comparing or fitting. You choose the metrics you want to use to evaluate these models, and then you just call the experiments to run all this for you. I don't know if I can get some help to switch into sharing my screen to discuss a little bit the code. And please feel free to reach to us if you have any questions about the code. All right, yeah, great. So we strongly recommend you to run it on Google Collab because we have tested it on Collab and it seems to work fine. So the first thing you need to do is to install Cornec. So here we use pip to install Cornec, but you can also install it from Anaconda or directly from the GitHub source, which are described in the Cornec GitHub repo. So for this first experiment, we are comparing 3 models. So as I mentioned, we first need to load the data here, which is the MovieLens 100K, a very popular data set for comparing and evaluating recommender systems. And here we choose 3 models. As you can see, like we just need to call and instantiate these 3 models with their parameters. Of course, here the objective is not to find the best parameters ever. By the way, Cornec offers you some hyperparameter search modules that helps you actually do some hyperparameter search in a very convenient way as well. So you can have a look at that if you are interested. And then we just need to instantiate the metrics that we want. As you can see, we can just do it in 1 line of code. And after that, we can call the experiment. And we have it. We have the comparison of the 3 different models in a very convenient and simple way. So again, feel free to reach to us if you have any questions. So if everything goes smooth, you should be getting the results of the 3 models in terms of the different metrics. I don't know if we have any questions at this point. Yeah. Yeah, sure. Thanks for asking. So MF is matrix factorization. PMF is probabilistic matrix factorization. So the difference with MF is that instead of representing every user with 1 embedding, 1 vector, we will represent it with a distribution over vectors. It's often more, let's say, robust because it takes into account the uncertainty we have about learning the user representations, especially in this context where often the user preference information is very sparse. So it's very hard to be confident about the representations that we learn about them. And then BPR is also a matrix factorization model, but here it's different in the way we train the model. So if you remember what Hady presented in the very beginning, in matrix factorization, we kind of use the least square optimization. We try to get the factorization close to the ratings, and we just minimize this distance. In BPR, actually, we try to give higher scores to items that we like. It's basically a ranking-based loss. Yeah. So the 2 models are the same. They use matrix factorization, but they are trained with different objectives. Yeah. Do we? Yeah.
So for the BPR, how do you convert the ratings to runs?
Okay. So actually, here we take the rating threshold, which will actually here consider that if the rating is greater than 4, then it's positive. And if it's not, it's lower than 4, then it's negative, actually. Yeah.
But then the MAE score, is it relevant anymore?
Yes, that's a very good question, actually. And this is why we put actually a question here. So let's visit the first question that I think would actually answer your question, which is very relevant. So the first question was actually to analyze those results and try to make some inferences based on those results. And the hint is that to focus on BPR compared to the other models. And what we observe actually, we have different metrics to evaluate the recommender models. And we have, for example, MAE, RMSE, which are basically just measuring the error between your prediction, or the distance between your predictions and the real values. And then we have other metrics such as NDCG, for example, precision and recall, that measure actually how good your model is at ranking good items higher. And what we observe here is that we can see like the MF and PMF model are doing very well in terms of MAE and RMSE, which are often called as rating metrics, but they are doing worse in the other or ranking metrics. And for BPR is the opposite actually. And the point of this experiment is just like to show you that optimizing for one metric doesn't mean that your model will be doing good in terms of all metrics. For example, if you take the matrix factorization model that optimize for the rating error, this doesn't mean that it will provide you good recommendations, as it can be shown here. Whereas BPR here, which just focus on putting good items higher, it doesn't care at all on the score that it predicts. Even if, let's say, it predicts 10 for a rating that should be 5, as long as that item is rated higher in the ranking, is ranked higher, sorry, then it's a good recommendation. Yeah. And then there is a second question, if some of you want to take some time, which is actually just asking to modify actually this code to compare the weighted MF and the BPR model, which are kind of a more fair comparisons, as a weighted MF doesn't necessarily focus only on reducing the error between the prediction, the predicted values, and the real ratings. If you have any more questions, please feel free. So at this point of time, we haven't looked at the other modalities at all. So those are the base models that later on we will enrich with some auxiliary data. I think we have some online questions, I guess. Yes. Yeah, thanks.
Yes, there are a few questions online.
Yeah.
A lot of questions online. Okay, so the first one is, can you build model ensembles with Cornec?
Model ensemble models?
Yes.
Yeah, that's a great question. At this point of time, I don't think we have ensemble models in Cornec. Maybe, not sure about that. We have been putting so many models, but it's possible, yeah. You can actually, and especially because we are having so many models, one thing that can be done, one nice contribution would be actually to try to combine predictions from all these models to make better recommendations. Yeah, definitely.
And another question is, going through the models in the Cornec repo on GitHub, most are named with 3-letter acronyms. Do you have a mapping between full model names and acronyms?
Yeah, that's a good point, actually. It's true that if you want to get the whole model name, I think there is, on the README page, we often try to put the titles of the papers there. But it's true, I understand that people who are actually very familiar with this model in the community. They tend to recognize them with the acronyms. But if you take a look at the documentation of the README page of the table of models, you should be getting more information than just acronyms.
Okay. Lots of questions are coming. I just choose one, and maybe you can address them
sure.
later on Slido.
Absolutely.
This one, for example, how can you compare the same model but with different hyperparameters? So
yes.
how do you know which is which?
The same model with the same hyperparameters.
No, with different hyperparameters.
The same model with different hyperparameters. Yeah. I mean, one thing we could do, you can see here, for example, on this notebook, when we instantiate MF, actually, we can just create different variables. And we can call it, for example, I'm just saying something very trivial like MF1, MF2, and then you instantiate them every time. So as you have a different name for the same model with different parameters. You may also consider taking a look at Cornec hyperparameter search to actually have results for the same model run with different hyperparameters.
Okay, thank you.
All right, I don't know if we have any further questions. Yeah.
Sorry, wait a second.
Sorry.
Because online they cannot hear, so.
Yeah.
I have a question because the additional models is about text, graphs, or images, but what if you just have a vector of values? Is that also in there with the easy library?
What if we have?
Just a vector of some values.
The vector of some values.
Yeah, so you just have numbers. So now it's really only text, graphs, or images.
Yes.
What if you just have values, a vector?
I wonder if you can give me a more concrete example. Let's say, like, you mean like for items, you have some...
Let's say for a user, you have the age, and you have the weight and the length. So 3 values.
Understand, yeah. That's a very interesting question. It turns out that in addition to this graph, image, and text modalities, we have an abstract class which is called feature modality.
Okay.
And in principle, as long as you can represent it as a vector, it can actually fit into one of the modalities. Even like, I mean, if let's say this is something that we will talk about when we talk about cross-modality. Let's say often like text, you can represent it as a document word matrix. You can just assume like your words may be other features like age or any other information. So it should not be a big deal to get it
so they're all
work.
translated. The text modality and the image modality are all transferred into a feature modality that can thereafter communicate.
Exactly, yeah.
Okay, perfect.
That's
Thanks.
the whole point, yeah. Welcome. All right, I don't know if there are any more questions. Maybe if not, I can hand it to Tuan, I guess, to speak about the text and image modalities. Yeah. Yeah, sure. So. Sorry, can you repeat, please? Oh, that's a very good question. So if you go to the WMF model in Cornec, there is a requirement file that actually says which version do you need. So by the way, like we don't handle dependencies in Cornec at the global level. So the dependencies are handled at the model level because those are evolving a lot. And every model is kind of independent to try to have a framework that is that enjoys slow coupling. So yeah, so every time, like if some model doesn't run because of some missing library, just take a look at the requirement file and it should be fine. Yeah, thank you. So I guess one, you can get started. So please take it over.
Okay. Hi, everyone. Okay, I think after that notebook, that tutorial, I think we can switch gear a little bit and start talking about our first modality, which is text modality. So, okay, so here we have this table. So in this table, we're trying to organize the model that have been developed with text modality into this map, and then it's easier for you to actually refer to them. So in the like each of the columns, we try to organize it in terms of how they model the preferences. Basically, it's a standard metric factorization, PMF, or factorization machine. The second column is like weighted matrix factorization, where mainly work with implicit feedback. Then we have APR and then NCF. For each of the rows, we present it in the way the text being modeled. So in the simplest form, it could be a term vectors, like a TF vectors or TF-IDF. Then it could be a document word matrix. And then later on, we have topic models, autoencoders, CNN, and then LSTM, those like deep learning kind of models. So that's also the sequence model that we are going to introduce to you. So this is the list of the references we're trying to add in here so that you can actually refer to them later. So let's start with one of the very first model trying to deal with this sort of feature. So in this particular example, I think they work with the other observability data. So they're trying to recommend songs where the auxiliary data is the album of the song. But if we have, let's say we have lyrics of the song, for example, then we can actually present it the same way. So basically we have each of the items gonna have their own feature vectors, and the regression of the rating values is the linear combinations of the features, as well as the part of the factorization there, which we have the user factors and item factors. So that is kind of the most simple model that trying to incorporate this information, and mainly you can actually work with text because text is like the most available one. So the other model we want to introduce to you is called the collective metric factorization, or CMF as an acronym. So in addition to the rating matrix, which is the matrix R there of end user and M items, that is the preference modality. So we have the matrix D, which is a span matrix of item and words. So now each items have their own text, right? It's presented as a document. So then we build a vocabulary of L words, and each one, each items can have a vectors of words that could be like the occurrence of the word inside the document, item document, or the importance of the word in terms of the FIDF, for example. So the idea here is like we try to factorize the two metrics at the same time, where if you take a look at the loss function there, the first term is actually, okay, so if I put the pointer here, so the first term here, you can see actually is the estimation error of the rating values, right? So basically this is the standard metric factorization terms. The second term is also a factorization, but for the D matrix, the items and word matrix. And if you notice here, the item latent factors are shared between these two factorization. And because of that, the information that learned from the word, the item word matrix actually influence the estimation of the ratings. So that's the idea of this model. So after we have that core factorization kind of model, we know that the text has been represented by topic model. So topic model has been very successful in modeling the text. So the whole idea of the topic model is trying to discover the latent topics of our text corpus. And you think about it, like each document is actually can be represented as a mixture of topics, and each topic have their own words distribution, right? So basically that is the brief idea of a topic model. And people actually trying to make use topic model to incorporate with the metric factorization framework for recommendation. And this result in the paper, collaborative topic regression. And this is CTR for short, right? This paper actually introduced in the KDD 2011. And this year, KDD actually this being awarded as a time award. Okay, so the idea of this paper is that we use the topic model to model the text. So assumption is that each of the document has their own text. Each of the item has their own text document. And in this paper, they experimented with the scientific articles, right? So a scientific article, each item is a scientific article. And so each of the documents, they're gonna try to learn the distribution of the topics over that document. And item. So the assumption here is that they want to pair it with the metric factorization. And the intuition is that two items that share a similar topics should like be recommended similarly. So for example, like some like preferences, right? So like some of the researcher actually focus on the particular topic, so they want to read like kind of like this, the articles that come from the same kind of topics. And another assumption is that the latent factor of the item shouldn't vary too much from the text, the topic distribution that learned from the text. So that is the two key assumptions of this model. And you take a look at the latent, the item latent factor is drawn from the normal distribution as well as also the user latent factor. And this is the generative process of the CTR model. So basically, the additional part here is the latent user vector U there, also drawn from the normal distribution. Whereas for each items, it's pretty much follow the same of the topic model, LDA topic models. In addition to that, there's a part of the offset. Epsilon here, which is it's also follow the normal distribution. But the idea is that this add up with the topic distribution of the item, the text item, to form the latent factor of the items to go into estimation of the preferences. And in this paper, that's the notional idea of adoption. So we can think of them as, if you work with the positive the explicit feedback like rating values, then that could be one type of the adoption. Another type of adoption is that you work with the implicit feedback like the clicks or other kinds of like implicit notion, implicit adoption. Then they have this notion of a confidence, where actually is, if you take a look at this, the adoption distribution is actually the confidence is the inverse variance of the estimation of the adoption. And introduce these two hyperparameters A and B. So if you can actually refer back to the building block that we introduced earlier with the weighted multi-factorization, it is a weighted multi-factorization for this part of the adoption. And so this is the learning objective of CTR. So similarly, we see that the first term in the objective here is the loss function here is trying to minimize the estimation error of the adoption, or you can think of it as a rating value could be. The second terms here is the negative log likelihood, right, of the topic models. And the third term is regularization of the user latent factors. The last term here is to enforce assumption that the latent vectors of the items B shouldn't vary too much from the topic distribution data of that particular item, learns from its text. So iteratively, we can actually estimate the parameters of the model. And for prediction, using CTR to make prediction, for existing items, we already learn the vector V of that item, so that we can actually directly make prediction with for each of the pair of the user items. Whereas for the new item that comes in, if we can have access to the text of that particular items, then we can actually try to estimate the topic distribution data of that item, and then we can actually make prediction as well. So for these CTR models, they try to experiment and then they show the result as compared to the standard collaborative filtering approach here. So we can see that with the text modality comes in, we see improvements. The CTR model is in green, actually performs better than the orange here, the standard collaborative filtering. Whereas with the LDA, which is like directly use the topic distribution of the items to make a prediction, then actually it's perform worse for in matrix. Meaning this one is the known items in the corpus. Whereas for the new items that comes in out of matrix scenario, we actually perform comparable between the CTR and the LDA model. Whereas for the matrix factorization, we can't perform our matrix prediction because we can't estimate the latent factors of the items. So that is the advantage of this CTR model, where we actually have access to text to the gold start items. So after the ideas of topic models, we start talking about deep learning. And in this particular model, we just talk about the idea of using so-called stack denoising autoencoder, which is one of the famous architecture deep learnings. And the idea is that, so using stack denoising autoencoder as a replacement for the topic models, for the LDA model in the CTR. And for this model, right? So the stack denoising autoencoder, the whole idea is that this by itself is the autoencoder, but there's a part where we're trying to corrupt the input. So that is the, and then we're trying to reconstruct the clean version of the input. So that is the denoising part. So to try to learn a more robust kind of representation of the text. And so with that building block, trying to introduce into a recommendation scheme, and this model called collaborative deep learning, CDL, which later on we can also experiment with in our notebook. So for this model, they try to learn kind of hidden representation of the text in the middle, and that representation is like a anchor points. It's like a topic distribution in the CDR model previously, and then that one they incorporate into the matrix factorization framework. And with that, they try to learn with the latent user factor to estimate the rating metrics. And that's the whole idea. And so for this one, it's also a probabilistic framework. So they also have a generative process for a user and item vectors as well as other components. But the whole idea is very similar. The only difference here is the replacement of the topic models by the stack denoising autoencoders. And then we have the same notion of the confidence score here because they adopt the same building block of the weighted multi-factorization. So that's the whole idea. And then this CTR model results in this loss function. So the first two terms are the regularization that comes out of the assumption of the distribution of the weights. And then the third term here we can see is that the minimizing the item vectors, the hidden representation. Basically, this is to enforce the item latent vectors to be close to its text hidden representation. Okay, the same idea. And then the fourth term here is to ensure that the reconstructed text is close to the clean version of the text. So that is kind of a regularization effect. But this is equivalent to the learning the log likelihood of the topic model, like we see previously in the CTR model. And then the very first one is the most important, trying to estimate the adoption, right? So that is the core idea of multi-factorization here. So with the incorporation of the stack denoising autoencoder, in the paper, the authors show that with a better architecture, the CDL can actually perform better than CTR. As you can see that in terms of recall, you can see the CDL is in black and then CTR is in blue. And in most of the experiments here, it performs better when you vary the M, which is the number of items to be recommended. And it's also performed much better than the other previous model. You can see previously like a CMF or SPD feature. And so they don't need to use very deep architecture here. As they reported that they use two layers of the stack denoising autoencoder, and they can actually achieve good performance. So follow that direction. This model called ConMF actually stands for convolutional matrix factorization. So as you can guess from the names, basically it's trying to introduce the convolutional neural networks to model the text part. And then they try to incorporate with the matrix factorization framework as well. So the only difference between this ConMF and the previous model that we introduced is that instead of trying to leverage the weighted matrix factorization in block, they actually make use of the PMF, the explicit version. It's trying to estimate the rating. So they focus on regression the rating value instead of trying to focus on the ranking metrics at the previous models. And yeah, so the replacement here is trying to replace the denoising autoencoder in the CDR model by the CNN. Whereas here they're trying to estimate the rating directly. So they focus on rating prediction problem. And the results in the paper show that these models, the ConMF, actually can reduce the error in estimating the rating values as compared to the two previous model like CDL and CTR. So basically, in this case, the CDL and CDR, they more focus on the ranking metrics, like the recall metrics actually. Whereas they also estimate, as ConMF can actually do a better estimation than a core building block PMF, which is a PMF. So that is without using the text as compared to ConMF. So those are the field of the model that's trying to encode the text into a kind of latent representation, and then with that, learn to align with the item latent vectors, then trying to do the rating prediction or adoption prediction. So in this paper, actually it's our paper, and actually in this paper we look at it in a slightly different way. So one of the key difference here is that in this paper we're actually looking at the text modality, but the text that we are looking at here is the review text. So it is not only about item text, but the review text is actually interaction between a user and items. So instead of trying to learn a latent representation, we actually learn a model in a generative way. So given a pair of user and item, we ask a model trying to generate the text, review text between that pair of user and items. And then with that user and item embeddings, which also trying to predict the rating values or the adoption between the pair of user and items. So with this modeling, you can actually see that we have images here, but the images here more or less actually trying to improve the quality of the text generated here. So to make the text more relevant and still trying to make the rating prediction better, as you can see a bit later. But that is the whole idea. And so that is the three components of this model. And you can see that really, if we actually use learned embeddings, basically in blue color, so we only have a user and item, so we're trying to learn the user and item embedding and trying to predict the ratings. Basically, that is similar to NCF model, and this is the error, the estimation error ratings that we can achieve. And then when we try to model the text, basically learning to also generate the text, and the text information actually influence the learned user and item embeddings, and with that we achieve better estimation error as compared to learning without the text. And when we try to input into the photos, the estimation of the rating doesn't improve much. As you can see, it's between the gray as compared to the orange. Whereas on the other side, like the second plot here, we measure the quality of the text, or how close the text, generated text, to the real reviews. And you can see that the so the blue one is only between the user and item embeddings. And then when we have the ratings, basically the rating trying to provide the sentiment signals to the text generation. and achieve better performance. And when we actually have a photo, the text is more relevant and more close to the real rating. But actually, that is not our focus, I think, as this in the context of recommendation, because we more focus on the rating estimation. Yeah, so just to give a couple of case studies that we have for the model I just introduced. So basically, if we take a look at this one is the rating estimation, and it's pretty close to the graph tooth here. So the above is the output from the model, and the below is the graph tooth rating. And here, given the same user and same items, if we actually input to different photos, you see that the text we actually output different item being mentioned inside the photo here, whereas the rest is pretty much the same. So this is another example where we actually have this kind of similar photos, but from two different users, given to the review the same item. So so basically one user review it with the positive review, whereas another one review with the negative reviews. And you see this is the rating estimation, and you can see that actually when the rating being provided to the text generation, you see that the generated text should reflect the sentiment here. The top here is good, and the bottom here is a bit too salty, where they actually trying to describe the same kind of dish from us. Okay, so those are the few text-based model that we introduced, and most of the model that we introduced there actually been supported with Cornec, and then later on we can actually try to experiment with that in our notebook tutorials. So I think we went through the text modality, and then now I think we can try to start talking about the second modality, which is image one. So similarly, we're trying to organize it into this source table, and as you can see that we actually have a less number of image model as compared to the text model, because you know that text is more available than image actually, and then just recently we focus shift a little bit to the images, and then we have a few work that actually explore the image modality. And so in the columns, I try to organize into kind of how they model the preferences, and then in the rows the same. This is how the image being modeled inside those recommendation model that we are going to present. So the first approach is trying to actually leverage the pre-trained embeddings of the images. And then the second one is actually trying to directly learn the convolutional neural nets, because you know that the convolutional neural nets, or CNN, is actually really good to learn the image representation, right? So these are the list of reference that you can actually take a look at. And one of the very first image model that we want to emphasize is called a visual BPR, or VBPR for short. So this VBPR model, as you also already see in the name, that is focused on images data, right? And so it's also trying to leverage the metric factorization framework, but for under the BPR objective. And under metric factorization, we have the estimation of the rating values between the product between the user latent vector and the item latent vector. In this case, the items also have its own image feature vector, which is extracted from some pre-trained model, CNN model. So it's this feature vectors has length D. So it's usually this image feature extracted from the CNN model have much higher dimensional than the dimension that we usually use in metric factorization, because most of us know that for metric factorization, we don't need to use very high dimensional to actually estimate the rating values. So in this model, they're trying to learn a projection E, try to reduce the dimension of the image feature to lower dimensions, then actually can try to fit into the metric factorization framework. So for each of the item, we have two parts. The part that actually learn the collaborative filtering signal, and the other part is trying to learn for the image features. And the intuition here is that the user preference is actually being influenced by two of these representations. So with that analysis, it comes down to the how we're trying to model the preference, trying to predict the rating value between a pair of user I and item J. You have the bias of the item, the multi-factorization part. This part is the visual feature that reduced into the low dimensional, and then this P is actually another user latent vector that interact with the low dimensional item vector that's projected from the visual feature to express the user preferences in terms of the visual thing. And the very last term here is more of the global bias of the visual feature. So more like the general popularity of the items, particularly this visual feature. So with such terms, we can actually try to make prediction of the rating value between the pair of user and the item. So then we can actually put into our learning framework, trying to minimize, because they try to make use of the BPR building block. So the input to the BPR model is actually trying to leverage triples. So because we know that BPR trying to preserve relative ranking, right? Preference between a user and a pair of items. And we also have the image feature that input to the model. And with that, to input can set up this learning problem. And then this is the negative log likelihood function of the model trying to minimize. So the first part here is the objective of BPR model. And then so we see that is the Rij here is between the user I and item J. Usually we also call that item J is a positive item, right? And this IL, so the L is kind of like a negative item in the sense that the item J should be ranked above item L with respect to the user I. So the following terms are mainly regularization terms with respect to the latent vectors as well as other bias and some other weight like the matrix E or theta in our settings. So with that way of incorporating the image feature into the model, this DVPR model actually essentially achieve better performance as compared to the building block of the BPR model. You can see that the VBR is in blue and the BPR model, the core building block here is in green. And then with the image feature adding, it can actually achieve a better AUC here. And then when compared to the rest of the other models, like another MF model, this is actually worse. So that showcased the influence of the visual feature to this recommendation setting. In the paper, the authors also demonstrate some of the visualization of the learned latent space of the visual feature. And you can see that there's some clustering effect here of the learned latent visual space. And that clustering effect actually in turn influence how the user latent vector also learns, right? Because it's learned to adapt to this kind of clustering effect, and then user preference also being organized in such a way to fit this clustering. And we can see that with the visual feature, it's actually has a big influence. So this paper on deep Bayesian personal ranking. So basically, this DVBPR is kind of like a direct extension from the VBPR. So the idea of this one is instead of using pre-trained visual feature, why don't we learn direct CNN to encode the image? And then so because we kind of like this one, we assume that we have more resources to train a bigger CNN, right? So we try to train a CNN to fit into our problem instead of using some pre-trained model, which is trained on some other task, right? So that is the general ideas. And As you see above here is the formula to estimate the rating values in the VBPR paper. For the VBPR, they actually also simplify the prediction. So the phi here is actually the CNN part. The X is the image of the item. And then it's project into the low dimensional vectors and then trying to interact directly with the user latent vectors. And that's it. So they observe empirically that just trying to do this simple estimation, it's actually improve the performance. So the remaining terms of the latent factors in the user multi-factorization framework, that's not necessary in this particular model. So that's a simplification. And with that, they actually trying to experiment with the this model on the same data set and compare with the VBPR, and then this simplification actually outperforms the VBPR settings. And one of the next model that I want to talk about is also called the visual metric factorization. So this visual metric factorization, so the difference between this model and the VBPR is actually how the objective here actually. So the VBPR, they leverage the VBPR building block, whereas the VMF, like the visual metric factorization, VMF, they make use of the metric factorization block, the MF parts, where trying to estimate the rating value instead of trying to preserve the ranking compared to the VPR. So the rest is pretty much the same, where we also learn the projection matrix E to reduce the dimension of feature vectors, and the F feature vectors here also between feature vectors similarly to the VBR settings. And for this model, they focus on the ratings, estimating the ratings, and then they measure the RMSE, the error of the rating instead of the ranking metric. This is another model called Attentive Collaborative Filtering, ACF. So this actually introduced like a new idea, trying to model the image morality. So there's this concept called item visual components. So basically each of the items is going to be integration of multiple components. And for the case of we have image of the item, then different spatial regions of an image will be different components of that items. And then if we talk about items at a video, then different frames will be different components. And then they use ideas of attention to trying to aggregate the different components into a representation of the items. And that actually trying to learn to model the user representation, in the sense that they look at the history of a user, how they interact with the other items in the past. And then with this attention component that aggregates different components, the item, and then they have multiple items, and then they aggregate everything together to form a so-called the representation of the user. And with that, they can fit into also the factorization framework to estimate the preference between a pair of user and items. And then with that score, they put into the PPR objective. So ACF eventually they try to optimize the PPR objective with the triples that we introduced earlier. So just want to highlight the key idea here is that trying to model the items by the multiple visual components, yeah, instead of feature vectors or an image itself. So this one I didn't show in the table, but I just want to introduce the idea that this paper from Sage, actually from Pinterest. So the objective of this paper actually trying to learn node embeddings. In this case for Pinterest, node would be image or the pin in Pinterest, but the direct application here is actually for recommendation, because standard recommendation done after we learn the node embeddings, the recommendation done by there is label lookup in the learn embedding space. But this one, the key component to learn the node representation actually is taking into account the item visual feature of the image, because for Pinterest they mostly working with images. So I just want to show some key ideas, and this actually make use of graph neural networks to learn the neural embeddings, whereas the input to the feature of the node is actually extracted from images. So I think with that, we actually went through a few of the notable models for image modality, and some of the models actually being supported in Cornec as well. So you can actually take a look and explore those models. So what time is that now? We can actually take a few questions before we do a coffee break, before we come back to talk about the next modality, which is a graph modality.
Yeah, so thanks, Tuan, for introducing these two modalities. I will go over the graph modality after the coffee break. So what we can do, maybe I let you handle if there are some questions online on Slido, and I will probably try to take some questions, if any, during the coffee break for the people who are here with me. And then we just continue after the coffee break. Yeah.
Okay.
Okay, so we will talk about the graph modality. So we will take a different approach in presenting some of the works that are leveraging this modality. So we will try to put a focus more on the main families that make use of this type of site information to improve recommendation. And then we will try also to give some insights of why it's important to consider this type of information for recommender systems, and also what families you should consider using, or how to choose the type of method you want to work with. Okay, so when we talk about graph data, it can either come from the user side, and this will be, we will be first focusing on the user side, and these are social relationships, like friendship, for example, which are often like undirected relationship between users. And so the way we will be representing this information is in a form of an adjacency matrix. This is the most popular way for representing this type of interactions. You can also have directed interactions, such as trust, for example. And again, like you may have an adjacency matrix to represent this information, but which this time will be asymmetric. Okay, now why is it important to consider social information when you are building recommender systems? It's because there are many studies that actually demonstrated with some empirical analysis that our consumption behavior is biased by our social connections. So the intuition is that knowing users' connections and what her friends like, we can help to better predict what that user actually may appreciate. And the main intuition behind the different models integrating this notion of social network is that the signals of user preferences can be explained by two main signals. The first signal is the collaborative filtering signal that encodes the user latent preferences, and the second signal is the social connections of this user, or the social influence of this user. So the objective of what is commonly referred to as social collaborative filtering is to actually capture user preferences from both signals, from the collaborative side and the social network side. So on the figure on the right that I took from this paper by Shanae al. that appeared at RecSys 2015, you can see some on the top. Those are the training items for the user in the middle, and then on the bottom, those are recommendations. And if you take a few seconds to analyze it, you will see that there are some recommendations that actually came from the user latent preferences because he interacted with some training items, and some other recommendations that actually came mainly from his friends. Okay, now what we will try to do here is to actually take a look at the different families for integrating this social information into recommender systems, or collaborative filtering models to be more specific. And the objective is not to review all existing methods. We will visit some examples of each family. But if you think that there is some method that is worth mentioning that we didn't talk about here, please feel free to let us know later, and we will try to update the slides and add the reference to that method. So the first type of method that we will consider turn out to be very similar to what we have seen with the text and image modality. We call them here feature-based methods. So the idea is to derive user representations both from the collaborative filtering data and the social network. And as you can, as we just saw, this social network can be represented as an adjacency matrix that can be treated as any other matrix, like document word matrix or an image feature matrix as well. So we can just use actually this general representation to represent the graph information. Now, the second family of method that we call here regularization based, those are the methods actually that take the model. They don't change the model architecture, but they just add some regularization to the model in such way as users that are connected in the social network have similar representations. Now, the final family that we will talk about, we call it here social network-aware architectures. So here you build a collaborative filtering model whose structure is aware of the social network. You don't necessarily see the social network data, but the architecture of the model itself is actually influenced by the social interaction of the user. Okay, so let's start with the first family, the feature-based approaches. So the big picture is like this. You have two signals, collaborative filtering data and social network. So both signals actually will help you to build the user representation. Then once you build this user representation, you can combine it with the item representation, for example, with matrix factorization to explain the ratings. So this is very similar to what we did with images and text, where for text, for example, you have a topic model to learn user representations from, or item representations from documents. And you can also learn item representations from the collaborative data. You combine them, and then you try to explain the ratings. Okay, the very simple model, actually, or one of the very first model that addressed this problem is called SOREC, Social Recommendation Using Probabilistic Matrix Factorization. So this is similar to the collective matrix factorization that Tuan has presented, if you remember. But let's analyze this graphical model here quickly. So we have two parts. On the left is the collaborative filtering part that tries to explain the ratings. And on the right is the social connections. So we have two matrices. We try to factorize them simultaneously with shared use and latent space. Now, here are the assumptions behind the different variables. So every circle here is a random variable of the model, and this is describing actually the architecture of the model and how the variables interact with one another. So for example, we see here that VG and UI try to explain the rating of user I for item G, and UI and ZK try to explain the interaction between user I and K. And if we want to see like how this user representation U gets affected by the two signals, we can take a look at the loss function and the gradient with respect to this user embedding U here. And we can see like in this gradient actually that we will be using to update and learn this factor. We see that the two information appear here. One is RIG, which is the rating part, as the other one is CIK, which comes from the social network. So this is a pretty good example that reflects this type of feature-based method. Now, of course, you can consider any model to represent or to learn user representations from ratings and social network. You don't have to use matrix factorization. So in this particular case, we are using the same model to learn from both data. Okay, now, why should you consider this model? It is simple and intuitive, and it turns out that it's very easy to implement. It turns out that if you just concatenate the rating matrix with the social network or the adjacency matrix, and you apply the PMF or the matrix factorization model on this concatenated matrix, you obtain something that is equivalent to the model we just showed. So you don't even need to develop a new model. If you have a PMF implementation, just concatenate your data and run PMF on it. You can perform very scalable training with SGD. It improves performance compared to the version that doesn't use the social network. And it can predict both ratings and social connections, which means like with one model, you can solve two problems. You can not only recommend items, but you can also recommend friends, which is cool if you are interested in recommending friends as well. But one side effect of this type of architecture is that if you are interested in predicting the ratings, but the social connections are too heavy, like they are much denser, you have much more information there, then your model may end up focusing on the right part instead of the left part. So you have to be careful when you are using this type of architecture, that the auxiliary data that you are adding or the graph modality that you are considering is not taking over the rating signals, which in the end are the focus of building a recommender system. Okay, now let's see a second example from the same family. So same spirit, but using graph neural networks. I think we have heard a lot about graph neural networks since this conference has started. So here, the same idea. We have a user that actually has ratings and social connections. So we use GNNs, graph neural networks, to represent the user based on the ratings, based on the social network. Then we combine these two representations into the blue one using some neural network. Similarly, we can use a graph neural network to represent the items. And then we combine the obtained user blue representation here and the item representation, pass it through some neural network, and predict the rating. So again, the same intuition. We are trying to represent users from two signals, and then once we have this representation, we combine it with item representation and explain the ratings. Okay, so just to look into a bit more details of how this graph neural network representations of user happens. So we have the two signals, ratings and social networks, and we are interested in user one here. So the first thing is we need some embeddings for the item embeddings and the rating embeddings. So for example, here the user rated items 3, 4, and 6. So we have the embeddings for their items, and then we have the embeddings of the ratings. Here, like to take into account really the value of the intensity of the embedding. So here, rating for item 3 is 4, for item 4 is 1, and then 5 for item 6. Now, we first project them into another space using some neural network. So we obtain some intermediate representations. We then combine them, and here this is the operation in graph neural networks. I think if you attended the talk by Max Willing last Monday, you have probably already heard about these types of operations, where basically here you have the parameters alpha that determine the importance of every node here. Since you can think of them as attention weights if you are familiar with the attention mechanism. Then we combine them into some unified representation. We can project it with some neural network, and it can be as simple as the identity transformation, which means like you don't have to apply transformations every time, but just to make it general, then you obtain this item-based user representation. Similarly, starting from this item-based representation, you can build a social-based representation of the user, and here they are indicated by the superscript I and S. And once you have this, you just need to combine these two signals to obtain the final user representation, H1 here, which is the representation of user 1, which is affected both by the social information and the rating information. You do the same for items. You obtain the item representation, and then you can explain your ratings. Okay, so here are some results from the GraphRec paper that actually demonstrate the importance here of having both signals in blue. It actually achieves the best performance. So here we are reporting RMSE, so lower is better. And then we see that the most important information obviously is the opinion, because when we remove it, which is the red bar, we get the worst performance. Okay, now let's visit the second family. So a lot of methods actually, here we have seen two examples for the previous family, but a lot of methods actually can be fit into this family. They are just using different models to learn from ratings and to learn from the social signals, but it's always the same principle. Now the second type of method, the core idea here is to bring closer. So remember this notion of having user and item representations. Here the objective is to say users who are socially connected should have a representation that are close in the latent space. And one way we can achieve this objective is by acting at the objective function level. Okay, so these types of methods usually have an objective function that looks like this. You have the first part, which is the collaborative objective, which is just basically any kind of collaborative filtering model can be there. Then what you do, you just add another term, which is the social aware regularization. And the job of this new term is actually to pull closer the representations of users who are connected. So one advantage of this family is that if you already have a model in place, you don't want to change it for some considerations, then it's cool. You just need to retrain your model and change your objective function when you retrain the model to integrate this regularization. So the advantage is that you don't have to do anything at the architecture level of the model. And it can also be a fast way to test if some information can help or not. If you want to know if your social information can boost your recommender model without changing it, maybe you can consider using this family first before considering using maybe a model that is, whose architecture is more suitable for learning from social network data. Now let's visit another example, again, matrix factorization based. So this model is called SOREC and is developed by the same authors as the SOREC we just saw from the previous family. So we have the collaborative objective, and we said we add a regularization term. So what happened here is that we are trying to make the representation of user I, UI, close actually to the average embedding of his friends. Feel free to take a few seconds to analyze this objective, but this is the main intuition. Another possibility is actually to do it at an individual level, which means like for every user, you try to make his embedding close to that of his friends actually. So here, UF here, it's actually all the friends of user I. Now, a different type of model that I developed when I was a PhD student is using mixture models. So mixture models, just to change a little bit from matrix factorization, mixture models are clustering models that you can also use to solve the recommendation problem. You can basically build clusters of users and then assume that users within the same cluster actually share the same preferences. So you can use the centroid of every cluster to make recommendations for users belonging to that cluster. So again, the idea here is the same. We have some mixture model, which is here based on Van Mises-Fisher distributions. We will not cover the Van Mises-Fisher distribution here, but it's basically similar to the Gaussian distribution, but on a sphere. It turns out to be a very good modeling assumption when you are working with collaborative filtering data. I invite you to take a look at the paper if you want to learn more about it and why it is important, actually. So here again, we have the log likelihood function of which we try to optimize when we work with mixture models, which is given with L here. Then we add the regularizer here. That depends on the social network. And then now we are interested in taking a look at this regularizer, actually, what it does. So in mixture models, for every user, you have these probabilities, ZIH, that actually represents the probability that the user I belongs to cluster H. So it's kind of soft clustering. It's not a hard clustering, though. What we try to do, actually, is we try to smooth these posterior probabilities based on the social network, which means like we want users that are socially connected to exhibit the same posterior probabilities over clusters. And once you have learned this model, and as you can see, we are not changing the mixture model, because in the end, when we will perform the prediction based on the centroid, the mu h of every cluster here, actually, we don't see at all the social information. So you see that it's involved in the regularizer here with tau ig, but at prediction time, you don't see any social network information. Okay, so here are some results from this work. So we have the social move MF here, which is the one that I just described. Then you have the move MF without the regularization. And also you have a number of other models based on matrix factorization and who are using social network. I just want to draw your attention here that it does not mean that because you are taking a recommender model, you are adding more information, that your model will be performing very good. The base model for learning from the rating information is very important. So what you should do, you should first consider of finding the best performing model just on the collaborative signal without any additional side information. So as you can see here, the mixture of von Mises-Fisher distribution that turns out to be a very good modeling assumption for collaborative filtering data actually outperforms the other models that even make use of social network information. So the key thing here is choose a good model for learning from your signals, then try to improve it using your social network information. Okay, now last we will take a look at the social network aware architectures, which may actually sound more fancy because we are seeing different models than the one we are used to. Okay, so the first model that we will visit is called social RBM deep. So RBM restricted Boltzmann machines are actually undirected graphical models. If you are not familiar with it, it's not a problem. The best way you can think of it is as an autoencoder. So what happens here, you have some user adoption, you project them into some latent space, hidden space here, H, and then from the hidden space, H, you can reconstruct, just as you do it in autoencoders, the adoption, which will actually help you to predict the missing adoption. Now, how can we extend this to integrate the social network information? Okay, so in this particular case, the authors actually proposed to add another hidden layer, which is here layer 2, and this is why it's called deep, because as long as it has more than one layer, we can refer to it as a deep model. So what is good to notice here is that this last hidden layer has actually as many hidden units as the number of users. And then for every user, actually, we activate only the units corresponding to his friends. So you see how the social network information here directly affects the architecture of the model. So you can take a few seconds as well to analyze how user 1 is represented here. Because he's a friend with user 4 and 3, so we activate his unit and the units of his friend in the last layer. As a second example in this family is something called social Poisson factorization. So the difference between this Poisson factorization and the factorization which we saw before is that it assumes that the ratings here are counts, such as clicks. So in this case, if you are dealing with counts, then the Poisson distribution is more suitable compared to the Gaussian distribution. And it turns out to be a very good model that I strongly recommend you to consider if you want to build some recommender model on clicks or even ratings as well, since ratings can be viewed as counts as well. So the main thing here is that we have the standard part of matrix factorization, which is here the item factors, the user factors that try to explain the ratings. But again, here we have something more. Now, the ratings of the user U for item I are not only explained by the combination of theta and beta, which are the user and item factors here, but also by the ratings of the friend of user U for that item, which are represented as RVI. Now, in addition to that, you have the tau UV. Again, it plays the role of some attention and normalized attention, which gives actually different importance for different friends, as it's natural to think that not all our friends actually have the same influence on our choices. We tend to be influenced more by some friends and less by some others. So this is a model that is also different and not common from what we always see in machine learning. So it's not a course about statistics, but In statistics, that is referred to as a conditionally specified model, which means like to explain the rating of a user for some item, you consider all the ratings given by the other users for that item, which is called conditional specification. Now, it turns out that this is an improper model, which means like we don't know if the likelihood function of this model exists. That is some technical detail, but it gives really good performance in practice, and it's quite scalable, and you can fit it very efficiently using variational inference. And here are some results. As I mentioned, this is a quite strong model, even if it's improper model, but it works well. And again, remember what we just said in the previous slides when we were looking at the results. The base model for your preferences is important. So you can see here that the Poisson factorization model here, PF, can sometimes do better than the other baseline that use side information. You can also see that the popularity baseline is quite strong as well. So you can also consider running that one first when you are building a recommender system and try to improve upon this model to make sure that your model is not doing good because he is just recommending popular items. All right, now we arrive to the item side. So we covered the 3 families of models for integrating this graph modality on the user side. Now on the item side, often we are looking for item relatedness. And the question is, how do we capture this item relatedness? One way is knowledge graphs, and we also have heard about them in some previous presentation in this conference. Now, this is not the only way we can capture item relatedness. Another one is what Hady mentioned in the introduction, is actually informations about which items are browsed together and which items tend to be bought together. So this is an information actually that can help us to understand how items are related to one another. Now, why is it important to consider item relatedness when you are working with recommender systems? It's because we rarely consume items that are actually identical. If we have bought, for example, a specific shirt in a specific color, we won't consider buying that item again and again. So we rather tend to consume items that are either complementary, such as a pair of shoes that goes well with a pair of jeans or a shirt, or consume items that are alternative with some different features, like different colors or things like that. So if we can understand how items are related to one another, even if I just have one interaction from the user, I can generalize his preferences to other related items. So it's quite strong signal to improve recommendations when you don't have a lot of user item interactions. And those are aspects of complementary items that are very hard to capture with the image and the text modalities. Why? Because image and text will tend to capture only items that have similar features. But obviously, a pair of shoes and the shirt, they don't have similar features. They are completely different. And you cannot, it's very hard to learn that they are complementary, for example, just based on the text or the image information. So in a way, the graph modality here on the item side can encode signals beyond feature similarity. And as we will see later, it's quite a strong modality compared to the other one, because it can reflect visual similarities, textual similarities, but even more. Okay, so again, we will visit few examples. We will not necessarily cover all the families. The first one is matrix co-factorization. It's basically SOREC, but you flip users and items, because now you have the network on the item side. So you just like factorize 2 matrices with shared item latent factor in beta here. So it's basically same as SOREC, so you can implement it again by just concatenating your item graph adjacency matrix with the rating matrix X here. You run matrix factorization on it, and you obtain MCF. Okay, another thing you can do if you want to improve the learning from, the item relations, which tend to be denser than the user-item interactions, is to use to combine the collaborative featuring model with a deep learning model to perform deep item representation learning. So the intuition here is that this deep item representation learning part will be guided by the collaborative featuring model to extract features that are useful to explain user preferences. Again, yeah, this is a bit specific of a deep learning model because it's not deterministic. It's basically every node that you see here is not a representation like in deep neural networks, but it's actually a random variable, which means it's a distribution. Now, the good thing to know about this is that it's more robust than running a deterministic neural network when you are working with data that are not very dense compared to images and text. Okay, again, here are some results that here we focus on this probabilistic collaborative representation learning model, PCRL. And a few things that we can see from these results is actually using the item graph does help. So here we have the model in red basically is like MCF, but using the Poisson distribution as the assumption for explaining the ratings. So you can think of it as co-factorization model. Now then we have PCRL, and the first thing that we observe is that the deep item representation learning seems to improve over just using factorization to learn from the graph. We also notice the importance of joint learning here, because the deep item representation learning part, you could have done it separately, like pre-train a model on that and then use those features to explain the ratings. But if you do that, your deep item representation learning doesn't know which kind of features to extract from the graph information. So it's important to perform joint learning. So as you tell your deep model which kind of feature can help to explain user preferences. As you can see here, the RL plus PF model performs quite worse, even worse than PMF sometimes. It's just because it doesn't extract the right features. It doesn't know which features to extract from the graph information. Okay, so just a quick question. In your opinion, if we were to put these two models into one of the above families, which one should it be? So obviously the feature-based, right? Because we are just learning user representations affected by two signals. Now we see another example, which is called collaborative context Poisson factorization again, C2PF. So again here, you have the matrix factorization model, same thing as we saw so far. And then you have another part, which this time says like, to explain the rating of the user, not only I take into account the user factor, theta u, and the item factor, beta I, but I also take into account the factors of the items that are related to this item. Which means like if I want to understand why the user may be interested in this item, maybe I better look also at how this user interacts with other related items. So if the user actually enjoyed a lot of these related items, maybe the model can guess that he's more likely to be interested in our target item I here. So again, this is an architecture-based approach. You don't see the graph information here. It's hidden in the architecture. It's reflected in the architecture of the model. This is a quite good performing model, and it does actually, so just here a little bit about the different variables. So here the context item factor is just the factor that represents related items. And then again, you have the context effect that measures to what extent every item influences the other items. And then you have the average context effect. It's actually the context, the effect intensity that you consider when you have no information. It's quite a good performing model, and it does improve actually quite strongly on the item recommendation compared to just the factorization part without taking into account the graph information. And sometimes the improvements are quite impressive, which highlights how important this notion of item graph is important. Okay, now we come into the final model that we visit here, which is called Knowledge Graph Attention Network, KGAT. So in this context, we consider that we have a knowledge graph on the items. And the key idea behind this model is to just treat the user-item interactions and the item knowledge graph as a unified graph. So this is what they call here collaborative knowledge graph. So you can see an example here. You have users interacting with items and then items related to some entities. What do you do then? You just need like to embed every user, item, and entity. Then once you obtain these first embeddings, you just actually run them through some graph neural network to obtain user representations and item representations that you can combine to explain the ratings of every user and item. So again, this is an architecture-based method because it just takes the graph and runs a method that takes into account the graph structure, actually. But in the end, you still obtain like user item representations that you can combine in some way, either using scalar product like in factorization method or pushing them through some neural network that will predict the user item interaction. Here are some supported, some graph-based models supported in Cornec. I'm not sure we have listed everything here. But just a few words before we move to the next hands-on is which family do you choose? I mean, you have seen that there are 3 major families. Most of the model fit into these families, and you may wonder like which one do I pick actually? Now, as I said, the first thing that you should consider is to pick a good rating model or a good collaborative filtering model that you can improve on. Now, regarding the families, it really depends on what types of problem you are trying to solve. If, for example, you are interested both in making prediction in the preference space and the graph space, you may consider one of those joint methods, such as SOREC or PCRL, that can make prediction in both spaces. If you already have a model for some reasons you cannot afford changing the architecture, you may consider taking a regularization-based approach because this will not require you to change the model, but just to retrain it, adding an appropriate regularization. Now, regarding the other family of models, based on my own experience, they tend to improve better. They tend to offer better performance. So if you are really looking for more improvements, you may consider also exploring some architecture-based methods. Yeah, but sometimes they may introduce some additional computational overhead, but they still remain scalable. Yeah, and here are some more references. So feel free to let us know if there is any specific model that obviously we can't. There are so many great works. And we can't, unfortunately, mention every work here, but please feel free to let us know if there's any method that is worth mentioning. Yeah, so thank you very much. And I guess I will hand it to Tuan for the hands-on part 2 on multimodality.
Hi, thanks, Aghiles. A lot of interesting model making use of the graph modality. I think we can start with hands-on 2, where we try to take a look at a few models, right? Of we have 3 modalities that we talk about. We talk about text modality, image modality, and graph modality. And in this hands-on, we will select a representative model for each modality, so to illustrate the concept. So if you have a slide, you probably have a link to access to this notebook. And this is on GitHub, but actually we try to make it runnable on Google Collab for use, so you don't have to set up anything, right? Similar to the hands-on one. So you go to this notebook and then you can click on run on Collab, and then it should lead you to the Collab website. And as you can see on my screen, I'm going to the Collab website here. So what I actually recommended to do is to go into the runtimes and try to run on first. So anyway, run all, let's make sure that everything's works the way it's designed, and then we can actually go through each of the part to talk about it. So just a brief overview that we're gonna go to each of the modalities subsequently, text modality, image modality, and the graph modality. So inside the text modality, we will take the collaborative topic regression, CTR model as an example. So we already presented earlier. So CTR model, we can use the topic models, right? The LDA as a core component to model the text, and then the weighted metric factorization to model the references. And that's the reason why in this particular notebook, we compare between the two. So the weighted metric factorization as well as the CTR model. So then the next part is about the image modality. So we introduce the BPR, visual based and personal ranking. And in this one, the BPR is the core component. So we compare that between the two models. So then for the graph modality, we talk about SOREC, right? But use the social network. In this case, we use the film trust dataset. There's a notion of trust, which is the between the notion between user, this user trust the other user. So we have an edge between the two users, and then there's a value, the trust value. So then that represent the graph modality. So then in this example, we compare between the SOREC and the PMF, which is the building block inside the SOREC to model the processes. Yeah, so that is a brief overview of how this notebook we designed. So please take a few minutes to run it and to play around with it a bit, and then we're gonna go through each of the block of the code here to explain more in details and then have a more discussion. So if you have any questions or any issue during the run of this notebook, then feel free to post Slido and or even offline there. I think Aghiles can also have to address. Yeah, and I think during the previous session, we also have quite a few questions and comments and Slido. We were trying to answer them online, but probably not all of them. So later on, if we have some time, and we try to address the others. Yeah. Yeah, I'm going to monitor the Slido. If you have any questions, feel free to post it there.
Yeah, so if you have any questions here, please feel free as well. So maybe one recommendation, you may consider jumping directly to the code. I don't think it's worth like spending too much effort on trying to understand the model details here, but it's just for your reference actually to get a sense of which parameters correspond to what in the model's objective function. Yeah, but I think you can pretty much skip the introduction part about every model.
We have a question here?
Yeah, sorry. Yes.
Just because I'm not familiar with the data, the Amazon clothing, what are the docs in this case? Is it the description of the items or the reviews of the user?
For this case, it's the descriptions of the items.
And is there like a recommended length that it shouldn't be more than that, or can you just give it anything?
It's actually not really. We just take the raw text, and then I think you can monitor it when you, depending on the method that you are using. So for example, if let's say you consider CTR here, which is using a bag of word representation of text, I guess you can control the size of the vocabulary that you want to use. Yeah.
Thank you.
Yeah, welcome.
There are a few questions from Slido.
Yeah.
Maybe I can start from the most upvoted ones.
Absolutely.
Okay, so for example, data on said modalities is sweet, but not always available. Would these models work also if text, image, or graph data is only available for a fraction of users or items?
In principle, yes. You can. It might depend on how different authors implemented the models, but in principle, yes. Nothing prevents you from using some sign information for some users when it's available and just ignoring it if it's not available. Yeah, definitely.
Another question is, did you use Cornec for huge data sets, and how did you do?
It actually depends, what do they call huge? Yeah, but I don't see any reason why it won't be running on huge data sets. It may also depend on the resources that you have as well, such as if you have enough RAM to load some large data sets, and because a lot of models will be optimized using stochastic gradient descent with mini batches. So this is a pretty scalable way of learning models. And none of them are not heavy models compared to deep learning models, so it should be fine. But obviously for this tutorial, we picked the smallest one to be able to run them quickly and see what's happening.
Maybe another question related to this one.
Yeah.
Is there any other way to express it? I think it is from a few minutes ago.
Yeah.
I think it refers to graphs. Is there any other way to express a graph other than to make a matrix? If I make a matrix, even if using a CSR matrix, the size of the memory I need becomes very large, even if the size of the data is a little larger.
Yeah, that's a very good question. So actually, I have showed the standard representation of matrices for the adjacency matrix, but which is actually often very sparse because most of the entries are 0. So often we don't store it this way in the memory. We just store it as a sparse matrix, which only reports what are the line columns interactions that are observed, and the ones that are 0 actually are not stored. So this is a very efficient way of storing this information. But of course, to go further, yeah, it would be possible to represent a graph in some different way. I see in some communities, they convert the graph to sequences and things like that. I think Max Welling in his talk, he mentioned about these types of approach on people working on molecule generation, where sometimes like they take the graph and transform it into a sequence, and then they treat it as a sequence using some appropriate sequential model. Yeah, definitely.
Maybe another one, which is Cornec compatible with both TensorFlow and PyTorch?
Is it compatible with TensorFlow and PyTorch? Yeah, so so this Cornec library is independent from other libraries, but of course it's compatible. You can use those frameworks along with Cornec, and actually every model has its own dependencies, and a lot of models, for example, they specify in the requirement file the dependency to some version of TensorFlow or PyTorch. Yeah, so it's completely fine if you develop a model with TensorFlow and you put it into Cornec. You just need to let know the users in the requirement file that they should have this specific version of this framework installed.
Hi, I have a question regarding the conflicting preferences between different modalities.
For example, let's take a specific example, like in movies recommendation system, you got some preferences on textual data, and for example, the system is hybrid, like it is speech recognition supported, and the user also said like I want movies with a particular actor or director, something like that. So how do you manage the conflicting preferences between different modalities?
Yeah, that is actually a great question. Obviously, this isn't the question that was covered by this tutorial, but often for the types of model that we have presented, there is no such thing. So, as I mentioned, there are, for some different families of model, may be affected more by this aspect. So, for example, if we take the joint model that trying to explain both the side information and the rating information, then obviously, yeah, there will be some conflicting information there. And you should be careful about balancing the importance of both signals. But if you take, for example, the architecture-based approaches, the training and learning is driven only by the rating information, which is your main source of learning. So in that particular case, you are obviously giving much more importance to the collaborative filtering side than the auxiliary data. But this is a very important research question, actually, to solve, to consider of how you should balance this conflicting or even sometimes some redundant information from the collaborative signals and the modality, the other modality signals.
Thank you. Just in addition to this question, do you have any idea, or maybe you observe some approaches that can help to identify or maybe analyze the conflicting preferences in a particular domain? In your specific knowledge?
I am fortunately haven't heard about that, but I will definitely try to have a look and see if there are some people that have focused actually on those aspects. Yeah.
Okay. Thank you.
Yeah. Welcome. Thank you for asking.
I have another couple of questions from the online Slido that maybe I can summarize like this.
Yeah.
Is Cornec extensible? I think that he intends, to add models or something like that.
Yeah.
And how do you think it is different from other RecSys libraries that are already available online? Like, for example, OpenRec, they talk about RecBall and all the others.
Yeah, that's an awesome question. So for the first one, yeah, definitely. RecSys is very extensible. I just remember a few years ago, we started with just one model, like PMF, and now there are over 40. And we actually, it's designed in such a way as you can add new models and new features very easily. And we do provide tutorials on the GitHub account, actually, that explains how you can easily take an existing model, even with an existing implementation, or write your own wrapper to make it available in Cornec. Now, regarding the second question of how Cornec is different from other libraries, so the focus of Cornec is really making it convenient to work with these models that integrate auxiliary data, such as images, text, and graph, which at the point when we started developing it, to our best knowledge, there wasn't such libraries that was focusing on these aspects. So when I say focusing on these aspects, is actually finding a way to standardize the implementations of all this model that may be using data sets, that may be using modalities that are completely different from one another, but find a standard way to implement these methods in a unified framework and to make comparisons both between modalities and models very convenient and straightforward. And you can find out more on the GMLR paper of Cornec that explains like really the point of this model and that position it compared to existing frameworks, at least at the time when we wrote the paper. I know things go fast in our field, So
I see another question that says that someone is having a few problems in using a dataset with 70,000 users and 500,000 items, and if you have any suggestion on how to solve this type of problems?
I think that's a tricky question because it's hard to say what they should do if we can't see what's going wrong. But the best thing to do is to raise an issue on the GitHub repository, and we are usually very responsive, especially to one here as well. So we regularly spend time to address these issues, and this can benefit other users as well. Yeah.
Okay, I quite a few questions already. Okay. We can actually go back and take a look at the notebook. So then just to briefly explain some meaning of some of the lighter quotes there. So then you can actually go on and then try with other models in Cornec. Yeah, so basically, regarding this, there was a previous question asking like, is Cornec compatible with TensorFlow and PyTorch, right? And basically, we don't make PyTorch or TensorFlow as the core dependency of Cornec. That is the first design principle that we agree in the beginning, and then we make those like the model-specific dependency. And as you can see here, in this particular tutorial, we have different models that use different library here. We have so-called the WMF model actually use TensorFlow implementation, and we have VBPR. The inside implementation of VBPR actually use PyTorch. Yeah, so we can have different models using different dependency. We presented and we say that we have the text modalities, right? In this case, we show the CDR model as an example, and we don't need to go into the model again. But one of the things that I want to highlight here is that it's very simple when you want to compare different models inside Cornec. And as we presented in the very first tutorial, that is experiment oriented, and saying that we basically construct a different models. With here, the objective is to make it easy to compare multiple models at the same time. Here we compare CTR and the WMF, and so the K hyperparameters here is the basically that is the latent dimensions, right? The latent factors, the user item in the WMF, and it's also the number of latent topics in the CTR model as we presented earlier. So here we train each model for with the iteration of the 50 epochs through our data. The hyperparameter A and B here to characterize the confidence score we presented in the way when we talk about the part of the basically this is a core part of the weighted multi-factorization actually. The confidence when we talk about the variance of estimating the adoption of the user to the item. The rest is like basic hyperparameters. We talk about a learning rate, and there's this lambda u and lambda v. Those also like hyperparameters of the regularization part. So lambda u is for the user latent vectors, as well as the lambda v is for the item latent vector. But in this case, to enforce the closeness between the item latent vectors and the topic distribution of each of the items. So basically, those are the important hyperparameters of the CTR model and also the WMF model. And when you want to compare those two models in Cornec, in this case we use the Amazon clothings, right? And see that we need the feedback between the user item, in this case the ratings, and we have the text, which is Aghiles, or we already answered earlier. This is the description, the text description of each of the items. And yeah, so we have each of the document correspond to each of the item ID status one. So inside Cornec, we have constructed the text modality to accommodate for the text. In this case, the text could be from user items, right? In this case, we show the text for the item side, but in some case, if you have like a user profile, for example, that's copy text, you can actually use text modality to model that as well. But here in this case, to construct the text modality, you can have you put the text corpus and the corresponding IDs. In this case, the item IDs. We have a bunch of utilities functions to process the text. In this case, text come in the raw form of sequence of strings. So you just tokenize it, right? Basically, we just tokenize it with the space and then remove some of the stop words. And we set the size of vocabulary to 5,000. We can change. Basically, we set it to 5,000. We have a relatively small size of vocabulary here to just basically make it run faster. And some other hyperparameters, basically just to filter some of like the common words, things like that. Yeah. So for more information, you can take a look at the documentation to understand the meaning of those parameters. And so we want to split the data, and in this case, we split it with the so-called ratio split. So we can specify the size of the test set, or also if we want to have a validation set, it's also available. The rating threshold is to characterize between the so-called positive or the negative feedback, because in this case, there's a notion that if we consider the ranking matrix, then we need to see which one actually positive and which one actually like negative items. Then we need these hyperparameters. Then when we construct the ratio split, we just input in the item text modality here and just specify that it's item text, right? So those models that actually model the item text can actually get access to this one. All right, and then we measure the performance by report at 50. Then after we declare everything, then we actually put everything together inside for an experiment and then run the experiment. In this case, we just put the evaluation method, which is the ratio split that we declared earlier. The two models that we want to compare are the CTI and the WMF. And then we put the metric 450 in, and then we run the experiment. Yeah, simple as this. And then when you run it, for the first time, basically the data is not cached locally, so we download it for you. And then as you can see here, you can actually take a look at here, and then you see some of the information about our size of the data, like the data, how many users, how many items, how many ratings we have there, the maximum value, minimum value, some of those information, right? And also the test data, and the total number of users and items. And after we train the model, run the model, and it's output the evaluation results on the test set. And as you can see here, okay, so basically the CTR model in this particular experiment is significantly better than the WMF model without the text data. And but you can see like there's a trade-off here, right? The training time actually takes a lot longer because the model is a bit more complicated, right? Because we need to model the text in addition to the preference. But basically, for the test time is pretty much the same. So that is a good thing, because during inference, after we learn the latent vector of the items, then the prediction is just the dot product between the two factors, right? So basically the same between these two models. Okay, so the difference only between the training. So that is for our first experiment with the text modality. Yeah, and the image modality and the graph modality basically pretty much the same. In this case, for the image modality, we use the same data set, because for this Amazon clothing, the different modalities are available, so we make use of that data set. For the image modality, what we actually provide here is the image feature. So it's already extracted from some pre-trained CNN model. So each of the items has its own feature vectors extracted from its image. So here we compare the VBPR and the BPR model, right? So for VBPR, we have the two K here. Basically the first K is the correlative filtering part, and the second K is the visual reference part. So that is the two size of the latent factors, and then the other hyperparameters are the same. Like we have a few of the regularization because we have a few different set of the parameters here. The lambda W, and the important part here is the lambda E as well. I want to highlight for this model, the VPR model, because it's quite important. That is the projection matrix between the item visual feature to the low dimensional items to estimate the preference. And this model is quite sensitive to this regularization. So if you play around with that, you can try with a few models. And in this case, as I mentioned earlier, VBPR implemented in PyTorch, so you can make use of GPU if you have it. And in this particular case, Collab actually have it. And then, yeah, so it's actually speed up the training of the VBPR model. And for BPR, we have only 1K, but we double the size, so just make it a bit more comparable between the two models here. And then, yeah, some other like the same iteration training. Then we construct the image modality, and then we put into the same ratio split kind of splitting. We specify the item image here, and then we put the image modality in. Okay, so because in the paper they report a UC metric, so here we also report a UC metric. And then we run the experiment with these two models, and then we basically after training we're gonna see the results of the two models. And similarly, we see the improvement here in terms of AUC. And again, we have the same kind of observations, right? The test time is the same because now you can actually see some general phenomenon here, because those kind of model, right, extend with some other modality, but basically the core component to estimate the preference is still metric factorization. So after the learning, what's retained is still the latent factors, and during the prediction, it's basically the dot product between the set of the latent factors. So it's pretty very fast, and basically it's compatible with the base model that is reliable. So that is a good thing about this family of model.
Yeah.
And
Tuan, we're having a question here.
Okay. Yeah.
Wait.
Go ahead.
Sorry. Otherwise, they cannot hear.
So is it correct that for the visual model, there's nothing specific to images? It could just be any modality with pre-trained features?
Yeah, so actually it's a bit related to some of the previous question asking like different modality. Actually, the underlying modality called feature modality. So it's different modality extend from that feature modality. So if you have feature, you can assume it to be any modality here. But this image modality should be able to support the images data as well, which is currently we haven't done that yet. But the idea is that if you have image data comes in the form of tensor, like 3 tensor, for example, it should be able to accommodate that form of data. But if you have feature, then you can ask people to as well. And you can see it's more clear later on when we move to the part of the cross model utilization.
Okay, thank you.
Yeah. All right. Yeah. So yeah, I just quickly go through the last part here with the graph modality when we experiment with the SOREC model, right? So SOREC, as you can see that the important part in the SOREC model is basically the key idea is the co-factorize of the two metrics, right? The rating matrix and the agency matrix of the social network, and they share the latent factor of the user, and there's this lambda C, which is to balance the trade-off between estimating between two metrics, the rating matrix and the agency matrix of the social network, and that is also a key hyperparameters of the SOREC model. It's quite sensitive, and then just want to highlight that is a part that we want to actually look at when you look at the SOREC model. And in this particular example, we use the film trust data set. I mentioned earlier that we use this with the social network, we use that to demonstrate the concept. And basically for the graph modality, you provide the in this case, the charts here in the form of the triple. Actually, here we can see here is the user ID, a pair user ID, and then the charts value. And then again, we provide into this ratio split. We specify the user graph, this modality, and then this select model can have access to this user graph. And then we run the same experiment. In this case, we report MAE because these two models, the PMF and the select, actually trying to do regression on the rating value. So then we measure the error, the absolute error of that regression model. So the result here of this model is quite comparable. We see a small improvement in some of reducing the error for the red model. You can see, and these two models, like the training time and the test time, are quite comparable because they even for the select, like the other part of the graph, learning is also a factorization type of model, so pretty much similar to PMF. Yeah, so I think with that, I want to conclude for this part of the notebook. Or if you have further questions, then feel free to ask questions. So, Aghiles, I think you can take over if there's any offline questions.
So, yes, do we have some questions?
Yeah, I have one question. Could you please go to the page where you trained the model and find out the accuracy scores?
Which page again?
Yeah, this one. Okay. So at first you calculated accuracy score, and then we have train and test columns. So I was just wondering, like, you have score 1 point something in test column. So could you please comment like what these scores?
This is a time. This is a time taken for training and test.
Sorry, what these scores actually represent?
The time was taken for the training and the test. The amount of time, so how many seconds? How many seconds?
Okay, thank you.
Okay. So that's the part that I was trying to mention, that during the test time, like they doing inference, this model, like the DPR and DPR, for example, they are not much different. So that's a good thing for this family of model, because after you learn a model, then the inference is pretty much the same. So the cost of doing inference is similar to the metric factorization kind of model.
Okay. Could you please go to the test results finally that you calculated?
Sorry, which one?
The results at the end of this notebook
For
the test data. Yeah, this one.
Yeah. Okay.
So in the test data, okay. So here you calculated MAE, and in the training data you calculated accuracy, I see. But there are some...
Okay, so the result here, the reported result on the test set for the two model, in the first column is in terms of MAE. We don't report any results on the training. The one that you see here, the column train and the column test here are the result, the time, how many seconds are taken for each of the model to do the training and to do the testing.
Did you conducted any analysis on underfitting or overfitting of the model?
Can you repeat it again?
Did you conduct any analysis on the model evaluation, for example, if it's overfitting or underfitting on the data set?
Oh, overfitting, underfitting. In this particular case, we don't have that analysis clearly, but what I can actually tell you is that inside this ratio split, for example, you can actually specify the validation size. So then you can actually have a fraction of your data to be a validation set. And then you run an experiment, and then you can actually report the results on validation as well. So then I think you need to monitor it yourself, like you're running a few experiments, then monitor that values. But in this particular case, we don't have an explicit mechanism to monitor that. But actually, in some of the implementation of the model, they also implement early stopping, for example. But that is like a model-specific implementation. And then they can actually monitor the results on the validation set. If you have that in your experiment, then the model can do early stopping to try to avoid overfitting.
Just the last question. What is the stopping criteria in this model?
Stopping criteria. For most of the model here is number of epochs. I think like most of the model basically just run for how many iteration or how many epochs that you specify when you construct the model.
I see.
Yeah.
But do you think this iteration is a effective criteria for the stopping condition? And how? Let me rephrase my question. Where did you get this number 50?
Oh, where do no, I think basically we try to run a few. We can't actually have a systematically search over this. I mean, in theory, you should have, to identify the best hyperparameters here, you should run for a few different ones. In this case, we just try to run a few and then to identify a reasonable one. You can test with other hyperparameters. And actually, in fact, in our library in Cornec, you have a function for hyperparameter search, and you can actually try to search for good hyperparameters each of the models. So you can actually specify, like, I want to search the number of iteration from where to where, or in which range, or in which set of values, and then that utility is going to try to search for the best hyperparameter for you. In this case, we just try to give a simple example to show.
I get your point.
Yeah.
Apart from the number of iterations, I mean, the criteria for the threshold of model loss is even better for in combination when it is used for the model performance evaluation.
Oh yeah. Some of the model actually implemented that, but that is like the model specific thing. We don't have control over that. Like each of the model, like some of the other contributors also trying to implement the contributor model themselves, and that is more of the specific implementation. Yeah.
Thank you.
Yeah. Thanks.
We also have an online question, which is it possible to run a significance test, a statistical significance test?
Okay, so that is very good suggestions. At least for now, we don't have that feature available in Cornec. Basically, you need to run the experiment for a few times, right, to collect the data points, and then you might need to do it manually, at least for now, yeah. So you don't have that feature for now, yes.
Yeah, so you basically need to add the loop, a for loop on top of the experiment and the models, and then you choose a different seed at random every time. So then you get like multiple runs with different seeds. This should do the job. You may consider also using cross-validation if you can afford it. This will give you some standard deviation there. At least it's a good indicator.
Yeah, so but basically we have very simple APIs to extract the results. So I think it shouldn't be difficult to do that. So you can run multiple times, and you have API to extract the results, and then you can run multiple tests with fast.
Maybe let's move to the last part, which is about cross-modality. So I think I would just be sharing my screen this time.
Okay, pass over to
Aghiles. Okay, so this is the third part. I guess you are already on the repo. So please feel free to open the third part on cross-modal notebook. So just to put a little bit of context, I think many of you have anticipated this aspect before, which is quite natural, is that we have observed in the literature that somehow there's multimodal recommender system have been developed along the modality streams, in the sense that people, they tend to call a collaborative filtering model that uses images, visual something, like the visual BPR. A model that is using text information, text something. And a model that is using social information as a social matrix factorization and so on. And the consequence of this categorization along modalities is that often if people, they develop a new model that is using text information, that they will only consider comparing to other models that have been experimented with text before. But as some of you have noticed already, for many of these models actually, if you just replace one modality with another one, the model will just be running, just fine. This may raises a lot of questions, like given a model, which modality should I consider? Let's say you have image, text, and graph. You may be wondering which of them should I consider? Which one would bring more help to improve the prediction of the user preferences? You may also wonder, like, given a specific modality, like, let's say graph, which model should I use to learn from this modality? Now, in order to make this kind of what we call cross-modality exploration easy to perform and to broaden the use case of existing models, we somehow manage in Cornec to make it convenient, actually, to run a given model with a different modality without the need to go into the code and change things. And this is important to consider because the modality that one model runs with may not always be available. Sometimes it may be missing. And also, it does not necessarily mean because a specific model has been experimented with text, it does not mean that this is the best model when you have text to learn from, for example. So in this last hands-on, we try to dive into this cross-modality exploration. So just to give you a very simple example, assume that you have a model, and let's make it a bit hard. This is the architecture-aware models for graph of items, for example, like the something like the social RBM deep or something like that. So obviously, in this case, you cannot just say, I will take, if I have, let's say you have images, but you would like to use this model. You cannot just say, I will take the image information and put it into this model. It's not possible because obviously it's a model that is designed to work with connections because it's reflected in its architecture. But one thing you may do that we support in Cornec is to transform your modality, which means like starting from the images. Let's say, for example, in the case of social RBM deep, let's say we have the images that represent some user preferences, for example, the type of food they liked or whatever, and let's consider that there are images associated with users. We can use them actually to build a KNN graph based on this visual similarity. And once we build this KNN graph, then we can take this graph and give it as input to our graph-aware recommender model. So it does not mean because we don't have directly graph data that we should not consider using this model. We can start from text or image, build a graph, and feed it to our model. And now, please take a few seconds if you want to set up the environment. I guess it's probably done if you have run the other tutorials. And so the first part is about using the CDL, VBPR, and MCF model with the text modality. So just to recall, CDL, Collaborative Deep Learning, that's a model that uses a denoising autoencoder to learn from textual informations. And it has been tested on these types of information when it was originally introduced. And then we have VBPR that we just experimented with in the last hands-on that was introduced for integrating image features into the recommender system model. And I just want to draw some attention here of why often with images we take pre-trained features, because it's relatively harder to learn from the raw images and map into map into the rating values. So it's often better if you can start from some pre-trained model or some pre-trained features for another task. At least you have some features that already have some understanding about the images. And then the last one is a co-factorization model, MCF, which has been used to factorize jointly an item graph and the social network information. So here we are taking all these three models, CDL, who was tested with text, in the literature VBPR with images, and MCF with graph, and we are running all of them using the text modality. And then, so this piece of code in Cornec shows you how it's possible to do it in Cornec without the need to go into the models and change specific things. So I invite you to take a few seconds to analyze the code. So the first part is just to load your data and split it. And then from that, you just need to build the graph modality, the text modality, sorry. One important thing, one technical details here, you need to keep some mapping when building this modality because you will be running multiple models. It's important to ensure that you have the same mapping across different models. There is not much to do. You just need to collect the item ID mapping here and then provide it as input to the different Cornec modules, especially the, let me see again, where you may need to specify this at the different modality levels to inform that every time you build a modality, you have to respect, you have to know the correspondence of every item. So if we take a look quickly here, so we build this text modality. And once we build this text modality, what we do, we take the count matrix, which is the document word matrix here, as a feature matrix. Then what we do, we can build an image modality that will be used by VBPR, but where we provide as input the term frequency matrix. And then for the graph modality part, it's a bit different, as I told you. What we do is that we build a nearest neighbor, a can-nearest neighbor graph from, again, using the textual features, which are represented as vectors. So there is this option of building the graph modality from features. So under the hood, it will be running some model to compute the KNN graph. And once you have built these three modalities, you just need to add them into your ratio split. Now, the reason why you should always specify those modalities in the evaluation method is to let actually Cornec handle the training, testing, splitting, and make sure it's having the right correspondence between the side information that should be in the training and the one that should be in the testing. If you don't do that, then you may struggle a lot in doing it manually. So luckily, you don't have to worry about this at all. And then again, this is standard in Cornec. You instantiate your different models, CDL, which uses the text modality, VVPR, which uses the graph modality, but, the image modality, but which is instantiated with the document word matrix, and MCF, which uses the graph modality instantiated by KNN graph built from the text features. And then you can choose your metrics and run your experiment. And then you will get some results. So obviously, we had a question here to do the same operation with the different modalities. But unfortunately, I think we are running out of time. So we will just go over this second part. So this time we take the same models, but we test them with the image modality. Now, one point of doing such experiment is to say, okay, if I have some image features, which of those models should I pick? Which one does better? And then again, same operation. You just need to instantiate the different modalities, image, text from features, and graph modality from features as well to build your KNN graph. Put it into your evaluation method, which is ratio split here. Instantiate your models, your evaluation metrics, and run your experiment. And finally, you can do the same with the graph modality. Run all the three models with the graph modality. So here again, you just take your adjacency matrix, treat it as a document word matrix for CDL, and an object feature matrix for VBPR, and then you can run all the tree model with this side information. So again, it's the same operations. Now again, we have done some visualization here to compare the different models with the different modalities and see what we can infer actually from this experiment. So what is, in your opinion, what is the first thing that we may notice actually? Because we have different types of comparisons. We have comparisons across models, and we have comparisons across modalities. It means like for every model, we run this model with 3 different modalities. So a first thing that we may observe, of course, we haven't tuned these models hard to obtain these results, so the assumptions may change, like if you find better tuning of the parameters for the individual models. But the first thing that actually we can notice is that you see the green bar here is always higher. And this corresponds to the graph modality. So you see like how fast we could tell that the graph modality is the one that is encoding the most useful information to explain the ratings. And that's one thing that justifies actually the importance of considering these cross-modality experiments. Now, one other thing that we may notice, for example, here, if we take VBPR in recall here, then it's doing much better with text than with image, even though initially it was introduced to integrate image features into the model. But luckily, as I mentioned, there is nothing preventing you in Cornec to use this model when it's possible with a different modality. And you can quickly check, run these types of experiment to check which model you should pick for which modality and which modality you should be considering. Okay, I think we can go back to the slides to conclude and discuss some of the future directions. All right, so as we have seen that multimodal recommender systems in most of the examples that we saw and most of the results reported in the literature help, but we also mentioned some tricky things that make sure you are first picking a good collaborative filtering model before considering adding any additional information, because adding more information doesn't necessarily mean that you will always be doing better than a model that only uses the collaborative signal. We just discussed about this cross-modality utilization, and there are many reasons that you may consider using it as the one that were obvious from the experiment, that the graph seems to be a better modality, at least in the cases that we considered. So it's important to consider this direction. And also, we talked a lot about Cornec, which aims actually to make these explorations around multimodality convenient. So there may be different future directions. Of course, the most obvious one is to consider more sophisticated model, and I'm pretty sure some people have done it already or they are doing it, is to consider more sophisticated models to represent each modality before integrating it into your recommender model, such as transformers or visual transformers for images. That is just one possible direction. Another direction is to consider other modalities that are underused, such as probably because they are heavier and harder to learn from, such as videos or songs, if you are considering a music recommendation, for example. And of course, as we have seen in this tutorial, I mean, different modalities can bring different types of information, and obviously it's important actually to consider, for example, integrating multiple modalities together instead of using just text, image, or graph or audio. You may say, you may think of a way of integrating all these modalities, but of course, this raises a lot of other research questions of how do you combine those modalities and how do you bring this heterogeneous information into one common space that captures user preferences. There are already some works on that, but it remains underexplored. There are already models, for example, that integrate text and social network information, but it's largely underexplored compared to the individual modalities. We have also talked about this cross-modality notion, and this actually raises the question whether we should consider developing modality agnostic models, which means like instead of focusing on one modality in particular, we always try to make sure that the model can accommodate different types, or at least can be generalized to different types of modalities. Yeah, and I think that is the end of this tutorial. Thank you very much for attending. These 3 hours were wonderful. Yeah, thank you very much for attending. And if you have any questions, I'm still around until the end of this conference. I will be happy to discuss more. If you have questions or if you want to discuss about other topics, please don't hesitate to reach out to me. Thank you very much.